So, good morning. If your head is not spinning yet from quantum computing, we try to increase the RPM a little bit and talk about organoid intelligence. This was one of the most fun and exciting stories I've done recently in the past years, and it also became basically the end of my book about the history of digital culture. And biocomputing is a very new field, and Steffi before, she made me pitch it in a second. So basically you take the best of nature to address the worst problems of, in this case, artificial intelligence. We're going to talk about it in a minute. Also, it's about energy consumption, which is the main topic here. And this is the future. I'll show you in a second also. You all probably heard the numbers that ChatGPT uses the energy of a small town, and that our human brain is still much more powerful and uses the energy of a 30-watt light bulb. So there's a certain gap between those two. And when I found Fred and his company FinalSpark, I was really excited about a new approach. And this is the fun of technology reporting, that you always find people who find solutions where you don't expect them. And because as journalists, we're trained to find problems, and you are the guys who find solutions. And so in this omnipresent age of polycrisis, maybe you guys can turn it around and make it into an age of poly-opportunity, maybe. So let's see the first picture, maybe, and try to convey what this is all about. We're going to see in a second. We don't. Well, anyway, tell me, what is an organoid?
So, well, an organoid is a collection of living neurons. And when I mean living neurons, this is what you see on the screen right now. You see on the left, it's a small ball of human neurons connected together. So consider it's a ball about 0.5 millimeter of diameter. So on the left, you see electronic microscope picture. And on the right, you see, well, in natural light, how it looks. And these are actually real neurons, and the purpose of what we are doing is to use them as a new type of processor.
So basically, I mean, how does it work? Is it because AI is running on neural networks that are built on the model of the human brain, and so we basically take it back to nature?
Yes, exactly. That's the interesting part of it, actually. When 30 years ago we started to do AI, basically it was artificial intelligence based on artificial neural networks. And what we propose to do today is to make the move back. And instead of using simulations of neurons, using real neurons.
How do you get an idea like that? I mean, it sounds very science fiction. It sounds more like a novel than a technology.
But first thing, I love science fiction. Yes.
Oh, okay.
But the thing is that we started our company. We wanted to make more sophisticated model of artificial neurons. Okay, because I have a PhD in signal processing, so I love actually mathematics and programming. This is my thing.
So your background is actually in physics and IT.
Yeah, absolutely. Yes. Right. So, but at some point we realized that if we take sophisticated models of neurons, we are consuming kilowatts of power. This is what we actually did for a few hundreds of simulated neurons.
Okay.
And at the same time, we had one of our colleagues, he was working at the EPFL, a Swiss Federal Institute of Technology, on the Human Brain Project, and he was actually measuring real neurons.
Okay.
So then the idea came, because on one side, it was measuring real neurons, and we had an energy problem. We said, okay, what about mixing both?
And just to go back to understand it, when you have a computer chip, it's very easy to understand. It's zeros and it's ones, basically. Still, how does it work on biological neurons? Is it impulse? I mean,
well, you'd better compare this to artificial neural networks, actually, okay? Because it's closer to this. Okay?
All right.
And when you see on the screen at the center, actually, you see I think here maybe 2 neurons, not more, but the rest are cables. Okay, so that means connections between neurons. So the basic functioning, I would say, very simplistically, is the same as artificial neurons. There are many connections, but each neuron behaves in a way more sophisticated way.
Okay. And they already exist. So one organoid, how many cells is in one organoid?
10,000.
10,000. So where do they live or reside, or what's their home?
Well, this is their home.
Okay.
So, I mean, so this is...
This looks like an incubator.
Yeah, this is actually an incubator. That means is an environment where we keep 37 degrees, 80% humidity, and 5% CO2. This is what they need.
So that's how we would feel comfortable as biological beings.
Yeah.
Okay.
Yeah. So, and what you see, all the tubes that you see here actually are fluids that are sent to the neurons to keep them alive, as we can see.
All right. So they're fed.
They are fed 24/7. Okay.
What do you feed them with? I mean,
we feed them. There are so-called mediums, okay, in biology, which are known to supply nutrients and all the vitamins, amino acids, salts, which are needed for support of life.
Mm-hmm. So you brought one of these. So this is like an apartment in the house of that,
yes.
to like put it bluntly.
Yeah.
And I see there's 4 empty rooms in there. I can give it a round if you want to have a touch. You can look at it, but if you don't give it back, it's not theft, it's kidnapping, right? So this is one of these houses where they reside in the incubator.
Yes, it's correct.
And if you look at it closely, it has 2 tubes running into, it has cables running into the cells, and it has 2 tubes.
Yeah.
So what are the cables for? What are the tubes for?
Well, the cables are for communication. Okay. So the way we communicate with these brain organoids is with electricity, with electrodes. So we have 8 electrodes for each brain organoid, and we can send some very small stimulation signals, like 1 microampere, and we are going to listen to their response. And this is this discussion that we try to master. And yeah, this is the goal of the research for the electricity part. For the tubes part, we have nutrients coming in and the rest coming out. And this is flowing 24/7.
Coming out is like defecating?
Yeah, I would say the equivalent, yeah, that you get, yeah.
So all this, they get fed, they poop, they live, they need certain conditions. Are they alive?
They are 100% alive. Actually, if you go on this website of our company, FinalSpark.com, you can see right now on the live section how our neurons are living. So you can see the signals coming directly from the neurons in life, fed from Switzerland.
Right. And if you feed them, it's kind of like a sugar watery thing?
Yeah, you need glucoses, but you need many other things, actually.
Like what?
Well, amino acids, for instance, vitamins, many salts. And, the field of electrophysiology has been around for 30 years. So we're relying on this research to build our biocomputer.
How long do they live?
Well, in the best case, we are able to reach 100 days, so 3 months, okay? Consider that at the beginning, we were like 1 hour, so we made big progresses.
All right. And what happens after these 3 months? You have to...
Replace them.
Replace them. Yeah. And then what is the biggest challenge in this whole process right now that you face?
Listen, there are challenges everywhere. Okay.
Right.
We only talk about things which are working, but for instance, contamination, they have no immune system. So if I've got one single bacteria in one of my operation, it's going to kill everything.
Okay.
In 24 hours, it's done. Okay.
And let's quickly see the next picture.
Yeah.
What does it do if you give them dopamine?
Yeah, that's the point, actually. I would say the biggest challenge that we have, the main one, okay, is training. And it's interesting because it's exactly the same problem that we had in AI 30 years ago. 30 years ago, because I was also working in this field, we had complex artificial neural networks, and we didn't know how to tune the connections between the neurons. And we found a way, which is called backpropagation, for those who know. And now we have the same problem, but this is with biology. And with biology, we cannot use backpropagation. We have to invent a new way to train the neurons to do something useful. So to reconfigure the network of neurons so that the output is what we expect. And this is what we are working on. And what you see here, basically, is one way that we use is to reward the neurons using dopamine. So we give a task, and if the task is met, then we release dopamine, hoping that the network will reconfigure itself. And what you see here is a bit flash, and this small flash actually is a UV signals that uncage dopamine molecules which are previously caged. So the UV radiation is just used to reward at a very precise time.
So now we have a living organism computing inside a machine. So one of the first questions that always came up when I talked about the story was, of course, how ethical is it to use human stem cells?
Well, yeah.
Something like that?
Yeah, this is a point-on question, actually. So, because these are human neurons, at this point we have 10,000, okay?
Right.
So, consider that it would be like a larva of a bee or something like this, okay? But there is no limit to what we can do here. We can have 100 billion, so as much as in a brain, or way more, actually. And what we started to do is to partner with philosophers and ethicians to work on this problem, about the ethics of this. Because we are not experts. I can tell you about the electrophysiology, but not about the ethics. I don't know anything about this. What I know is how to discuss with these people, give them the knowledge, and they have to think about it.
And the stem cells themselves, is it ethical to use stem cells now? I mean, there's been debates in...
Yeah, well, not this type of stem cells. So that's interesting also. Professor Yamanaka in 2012 got a Nobel Prize because he invented a way, to take cells of your skin and to turn them into so-called induced pluripotent stem cells.
Okay.
So we can now change these skin cells into pluripotent stem cells, and from pluripotent stem cells we can do any cells of your body, including neurons. This is so we are using the neural cells.
So basically, we can recycle dandruff. I mean, it's not my problem, obviously, but we could use dandruff and turn it into these usable stem cells.
Yeah.
What are the? I mean, since we're in the realm of science fiction, at least it feels like it. What are the chances that from these organoids, that at one point they become autonomous, also biologically, and they turn into living beings that we can't control?
So, from a theoretical perspective, it could be possible. There is something that we have to consider. It's possible blending between AI, I would say, and what people call OI, which is organoid intelligence. So this may come at some point, and robotics, which is also needed to be autonomous. And this blending, since it's biological, can come also even to human beings. Interacting with human beings may be different with this type of biocomputers. So it's a whole new way of considering the world, not only of computation, but interaction with machines, which is coming here.
I'm not sure if you calmed down the some of the worries in that field, but well, I mean, do you think it could become sentient?
What we are sure is that nervous tissues are able to process information. Okay, they have been created by nature and refined for 300 million of years to perform this. So it's probably the most efficient way to process information. So does it mean sentience? This is an open question, and not actually for me, but more for philosophers and people who are in the know.
All right, we'll circle back to that in a few years. Well, for now, these organoids are very small. There's 10,000. I mean, if you look at this little element here, you'll see how small these still are. what can they already do something? Are they just in existence as a theoretical experiment, or can they already do something?
Well, at this point, I'm supposed to try to show you something.
Okay. All right.
But
so they are working neural networks.
Yes.
That are beyond theoretical experiments.
Yes.
Okay.
What we are doing actually is really using real neurons. So.
Oh, there you go. So what do we see here?
So what we see here is basically a live connection between a simulation of a butterfly running in this room and interacting with our neurons in Switzerland.
So these are 4 live neurons, right?
Well, these are
organoids?
These are four brain organoids, and we are interacting with one of these.
Okay.
And this is how actually, at the beginning of this demonstration, you saw the butterfly coming directly to my cursor here. It's because it sensed the presence of my light, and through the interaction with the organoids, so 1,000
And what are these spikes?
Yeah, these spikes, this butterfly is moving randomly.
So it's basically like a video game.
Yeah, purely stupidly randomly like this. And if he sees the light, then he's going to send some signals to Switzerland.
Okay.
If Switzerland answers, if the brain organoid is in Switzerland, then it stops moving around and goes straight.
Okay, all right.
So from a scientific perspective, I mean, this is not a revolution. But from a technological perspective, this is working for real. So I showed it, okay? So there's this difference between something that in theory is easy to do and something which is actually working. Right. So real-time interaction through the internet with the living human neurons.
Right. It just stopped.
Yeah, because
so can people go to this website?
Only allowed 1 minute.
Okay. Of course, I mean, the video games, during my research, I came across the video games are the most kind of visceral way of understanding that something works already. I think your colleagues in Australia made one of these organoids play Pong?
Yeah, we have also, well, this is a new field, okay? So basically, we are 3 companies in the world. So would say competitors, but I'm happy to welcome other ones because, and indeed, it was
3 companies only.
Yeah, 3 companies are that's all.
So
okay.
Are your organoids already used by other people, like science?
Yes,
scientists?
well, yes, that's cool that you tell me about this because there may be some people from Munich University here somewhere. Yo, so hello.
Oh, we see hands there.
So I'm happy to see you. These people here have been using remotely our brain organoids for several months already, because what we did is that we connected this to the internet, not only to play butterfly, okay, but also for researchers. So researchers can connect, we give them Python interface, and they can stimulate and listen to the neurons and do some research. So, and we have 9 universities at this point, working 24/7 with our brain organoids. This is why I had limited time, actually, and doing some research in parallel. So and this is called the Neuro platform. It's a platform of open innovation of research in this new field.
So if people want to experiment with it, they can contact you through the website?
Yeah, absolutely. We have also a Discord server where anyone can ask questions, and if they want to propose a project. Right now, I think we have like 100 candidates to use the Neuro platform. So, but
there's a wait list.
But for universities who are proposing projects, okay, and if they accept to share the organoids with others, then it's free access.
Okay.
But there is some selection.
Right. So this is very, you work with science, and so a lot of it's shared. But you're a company. You're a private company. You're not an institution.
Yeah.
How scalable is it at this point? I mean, what is the time frame you think it can be?
I think
in more general use.
I believe that in the next 13 years, what we want to
30?
do 13,
13.
Okay. What we want is the equivalent of Amazon Web Services, using it's like biocomputing, I would say. So imagine that you are able to serve customers with a layer of diverse tissue, like 100 meters by 100 meters with several centimeters. We believe that with this, we could make a profit of over $1 billion per year in 13 years.
Okay. Yeah. So who's financing this project right now? You?
Well, that's the point, yes. This is our second company. So the co-founder and myself, we created the first one, which makes enough money to finance this one, but we don't have enough money to scale this to this size. So we are looking for 50 million and still looking.
Oh, okay. Anybody?
So,
your other company is also in AI, right? It's product identification?
Yes, it's used to detect counterfeit products using smartphones.
Right. So we're out of time, but just briefly, what is your vision for biocomputing and organoid intelligence in the next 10 years? Where do you think it's going?
It's going to change the world, for sure. It's going to stay, for sure. This is not going to stop because this is 1 million times more efficient, energy efficient than a digital processor. So it's going to be a revolution.
Well, you heard it here first. Thank you so much.